let me get started. I'm going to begin with the promised overview of what I hope to do for the next most of the term. And so what I have here is a table showing basically the sort of the results and the techniques for the problems we want to discuss. And so along the left-hand column, there are various phenomena. On the right-hand column, so here E is Euler, and GP is gross PTSD. That's pretty clear. And so these describe classical and quantum fluids, respectively. Okay, and so the absence of, say, one of the equations in some of these lines indicates that there aren't really any results about it yet. And so, for example, in the first, as I mentioned before, for this problem of rotating points that we've considered, it's not really clear if there exist rigidly rotating solutions of the gross potential equation with a bunch of point forces. Okay, and so just to give like a general overview, and so, okay, well, if we look at this, the first batch of phenomena are all ones involving solutions that move by rigid motion, so either a rotation or a translation or a combination of rotation and translation in some cases. And so these all reduce to basically elliptic problems. So they reduce to problems in which the time variable doesn't appear. And in general, there are two, so CV is calculus variations, PD is PD. Generally speaking, there are two kinds of techniques one can use to do this. One is what we've seen. So recast the problem, it's a variational problem, and then study minimizers and show that they indeed yield a solution of the Euler equation, of the equation in question, Euler or gross PTSD. And the other are more, say, PD techniques. We'll see what this means in practice when we look at an example in detail. But these might mean, well, yeah, they're pretty different. But I guess the point I want to make is I want to cover at least one, in some detail, one proof of each type. And so what we've done so far is we spent some weeks, a couple weeks really, talking about a calculus variations approach to the Euler equation. And I want to do one PDE result. I think the one I will do is rigid vortex helices for Euler. And this is a very recent result. This is a result from within the last, I don't know, 2 or 3 months. Hopefully it's, at least the main ideas can be presented here. Probably not all the details, but I want to give at least a feeling for how this goes. And so well, we'll see what the difference is, but so here these are really constructive techniques. In fact, I used the word constructive below. And so the PDE in question will be a so-called semi-linear elliptic PDE. So it'll be a Laplacian of psi is equal to f of psi for some f. And then there'll be some other terms, some forcing terms or some gradient terms. But what one does is one starts with basic solutions, like we might have an entire solution on R2 of this equation, Laplacian psi is equal to f of psi with good decay. And then one tries to glue those together and to linearize them around them and so on, and use elliptic theory. We'll see an example. So we'll do that for sure. I may or may not do an example for, in general, my bias is that the problems involving dynamics are more interesting. And so the ones I want to focus on are the ones below this line. Okay, but we may do, for example, something like this. No, I guess to do something for gross PTSD, maybe. Okay, and these, I should say, these rigid vortex helices, these are solutions, these are 3D solutions in which the vorticity lives along a helix, and it moves by a combination of a vertical translation and a rotation. And so these are mildly exotic solutions, and we'll see if we can construct those. Actually, I believe I made a mistake here, because this is this paper's kind of new. I don't think this has been done yet. I don't think there are any calculus variations proofs of this result. or any approaches. For all the others, well, I guess there are for Gross-Pitievsky, but for Euler, no. Okay, then, so that's, and so the goal is both to examine a variety of phenomena and a variety of strategies of proof. Okay, so let's move down here. And okay, so 2D point vortex dynamics, we'll take that up today. And so this can be done via, for Euler or Gross-Pitievsky, there are known results in both cases. For Euler, there are both. So this is the proof I'll present starting today, what I've called estimates plus Grunwald. Well, we'll see the strategy. So this will say, take a solution with certain initial data and then do some work to try to prove estimates to show that it remains, so that the initial data will be concentrated around, we'll have vorticity concentrated around a bunch of points, show that, devise some functional that measures the extent of concentration around points and control the growth of that functional. That's the basic strategy. And so this involves estimates and then some kind of, some argument, a differential inequality for the energy. Okay, there's a different approach. And so these results, these ones are from the 80s and 90s. Let's say 90s are the first decisive result, but there continue to be papers written on this, actually pretty good papers written in the last year or two. So this is an active topic of research. This is, there's only one result. And so here again, these guys have a constructive approach. They start with, so they want to construct solutions to the Euler equation with these point vortices moving around. We'll see what this means. And they really sort of build them by hand. They build a good approximate solution and then they adjust it to get an exact solution by using elliptic estimates and so on. So, so this is very, very recent work. Well, within the last few years, it's a kind of interesting approach. And so they work a lot harder for the constructive approach than the one I'll present starting today, the Grunwald approach. They work a lot harder. In some ways, their results are weaker. So they can handle only very, very special initial data, whereas the other approach can handle much more general initial data. On the other hand, for the special class initial data they get extremely precise description of solutions. And so the different approaches have different advantages and disadvantages. The reason I want to discuss this PD result in vortex helices is that this is really too hard. So this is too hard. It's like a 50-page paper, whereas, as we'll see, the other proof is easy, it's short. But this PD argument up here for vortex helices gives you an idea of the character of these kinds of approaches to these problems. Okay, and so the reason we're doing this will be as a proxy for the more interesting but more difficult and technical result on Euler. And then I'll try to do this also, a Gross-Pitievsky result on point vortices for the Euler equation. And so here, calculus divisions appears because clearly we're not minimizing a functional, which is the sort of the origin of the calculus versions. But it ends up that one is considering, I mean, somehow the argument, well, actually, we saw this already in what we talked about last week. That at some point it's so in what we saw in this variational proof, not only were there arguments where you minimize or maximize things and compute equations for maximizers, but also there was this vorticity concentration lemma which said if we have some constraints on the vortice, if we know its integral is 1, it's non-negative, and so on, and if the energy is close to the maximum energy, then it gives us some information about what the vortice looks like. It's close to being a ball of radius epsilon in some ways. It's rather concentrated. And so this is a kind of variational argument that says that applies not only to maximizers, but it says that if things are near maximizers, then you get some kind of quantitative information about what they're doing. And those things are very useful here. And in fact, in every proof about dynamics for Gross-Pitievsky, these kinds of estimates are needed. And this is a kind of a substitute for the Biot-Savart law, which is not available for Gross-Pitievsky in the Vorticity transport formula. Okay, so we won't do this. And so the goal is to do things that have little purple arrows pointing at them, to discuss this in class. Okay, ring dynamics. I'd like to talk about this if there's time permitting. And so in some way, the proofs here are I mean, one way to think of it is that they're like the 2D point vortices, but more technical. And so if time permits, we'll look at some of these in detail. My priority would be Euler. And so the reason Euler is a priority is that, so the most interesting phenomenon, and so here we're looking at basically vorticity with cylindrical symmetry in 3 dimensions, rings. And so the most interesting phenomenon is this vortex leapfrogging, which I showed you a video of a while ago. Let's see, I can find it quickly. Well, let's not bother. But so you may remember this video. This has not been proved for Euler. This has been proved for gross Vortices. There are theorems that say this happens. And so for Euler, this is an interesting problem. And among the difficult problems I'll mention, this is probably the least out of reach. And so when I say less known, I mean in particular that has not been verified for Euler. It has been verified for gross Podolsky. But this is a pretty technical result, and the problem is finished, or at least that part is there's more to do, but that's technical. So I plan to concentrate on what's known. So there are weaker results for Euler that don't establish leapfrog, but they establish something. And so we can discuss those. Those actually reuse a lot of the ideas for this, and so we may be able to do it quite efficiently. That's my hope. Okay, and then, excuse me. Then the next situation is, you may remember I showed you a video of an airplane on the first day. The airplane with these 2 vortices coming off the wings. And then there's some asymptotic law that's supposed to govern these vortices who are, say, rather small perturbations of a straight line, and then you can have multiple ones who are a rather small distance apart. Okay, so this is nearly parallel. This is dynamics of nearly parallel vortex filaments. Again, this is known. There's a theorem for gross Podolsky, and for Euler, it's completely open. So, and this too isn't. So let's say time permitting, we can say a bit about this. The whole proof again involves tons of input from the calculations, which takes time to do in detail, but we'll say a little. And again, for Euler, this is interesting. Probably close to impossible as things are at the moment, but it'll be nice if one can prove anything. And then finally, the most general question is: suppose we have a vorticity concentrated in 3. Well, actually, not quite the most general, but the most general for purposes of this class is: suppose we have vorticity concentrated around a nice smooth curve in R3. And I solve one of my equations, or gross Podolsky. I study a classical or quantum fluid with this initial configuration. And what one would like to believe is that this is I would say, called a conjecture. The vorticity remains concentrated around that curve, around some curve, and the curve evolves by a certain law of motion, which is this thing I've referred to as the binomial curvature flow. And okay, and so I certainly have to spend time talking about these. These are again, well, I mean, they're results in both what I've called conditional results. In other words, these are barely results at all. They say if you knew all this extra information about the solutions, then you would have a theorem. And so the way I see this is these identify the binomial curvature flow as the only possible law of motion for vortex filaments in this setting, but they don't. They fall far short of proving anything. Nonetheless. And so here the mathematics that's involved is actually, in some sense, a geometric measure theory. It's sort of a weird application, at least a perspective from geometric measure theory. And so, right, and so we want to see both the calculus variations here, PDE, calculus variations used to obtain estimates that are then used for dynamical problems, and the geometric, and so the last sort of techniques, will be these, and then this equation itself, this geometric, so this is a geometric evolution equation, which describes a way of curves evolving R3. It has very interesting properties, and so that's worth discussing on its own, which we'll do. And so, so these are the plans, and so you can see that I want to give a survey both of sort of specific problems within this domain and techniques used to approach these kinds of problems. This is the plan. And so especially if you're a student in this class, I said that I will ask you to see if you can work on some kind of problem connected to some sort of research question. And you may think about which of these appeal to you. There are open questions in every one of these domains. Some of them, I mean, here I would say, well, I wouldn't say they're all impossible. But let me mention, if you want, I mean, this is a little bit silly, but okay, here there's this, right, this leapfrogging has never been proved for the Euler equation. If you want to, you could call this a 160-year-old open problem, because this phenomenon was first described in a paper of Helmholtz in the 1850s. And it's been the subject of and he described it in kind of a qualitative way. People worked on it throughout the 19th century and the 20th century. But a rigorous proof is still missing 162 years later. I think it was published in 1858. And of course, it's not like the Riemann hypothesis where all the best mathematicians have been working on it since it was promulgated. But nonetheless, I mean, in some sense, it's a very open problem. These two are and these are harder. This for Euler, all of these are sort of well-known and difficult problems. And so these are, and so you shouldn't expect to be able to just sit down and prove the theorems. But there are many interesting things to work on, and one may be able to identify useful technical ingredients that would help elucidate our understanding of many of these questions. Okay, so students in the class. And I'll distribute via the U of T Quercus system something written about possible topics and how you should contact me about that. Okay, any questions? Then do this. Okay, so, good, that's what I want. Okay, so seeing no questions, I'll move on to the next topic, which is 2D point dynamics for the Euler equation. So this will take, we should be able to do this, we should be able to do a more thorough job. So I skipped some details on this rotating solutions. Actually, let me go back here for a second and say, well, yeah, a lot of these variational arguments have a similar character. And for some reason, this translating vortex ring was the problem that historically captured a lot of attention. And so this was, when the first solutions were constructed, it was like a 50-page paper in Acta Mathematica in one of the top journals in 1972, a long time ago. But yeah, these all have a rather similar character. And so having done one in some detail, I think we won't do much more in that direction of the variational approach to the Euler equation. But there are interesting questions for students that you might consider. Okay, and so then moving on to 2D point vortex dynamics for the Euler equation. And so let me remind you of this setup. We again have this, so let's fix some non-zero numbers. So these will be what I want is to imagine a point vortex. This is the ODE that's supposed to govern point vortices. we gave a kind of a formal discussion leading to this some time ago. And so I have vortices P sub little m, where little n runs from 1 up to capital M. And so this says that each vortex generates a rotational velocity field that falls off like 1 over distance, and it has a strength of so this the sign of the gamma. So there's this gamma L will be the so sort of the strength of the Lth of the velocity field generated by the Lth vortex. It falls off like so. This gamma L will be, if gamma is positive, that means a counterclockwise rotation. Negative means clockwise, and then is proportional to the size of gamma. So each vortex generates such a velocity field, and then each vortex is convected by the sum of the velocity fields generated by all of its neighbors, all of its peers. And then they start at some initial, we have some given initial conditions. Okay, I'd also like to, so I want to, so my goal is given, so I have all these points moving on the plane, given by an ODE. And my goal is to find solutions to the Euler equation who behave in a similar way. And for this, one thing that can happen is that for this ODE, this point vortex ODE, it can happen that 2 points collide in finite time. When that happens, the dynamics is no longer, I mean, I have a, the dynamics is no longer smooth. It's kind of a blow up. I have a, if PM minus PL goes to 0, then this denominator behaves very badly, and I don't know what's happened. So that can happen. It won't happen right away, for sure. And so let me assume that at least I have some interval from 0 to t star, such that on this time interval, no two vortices ever collide. And let me also remark that this collision, that for generic initial data, you will never see a collision for generic initial data. This solution has this ODE has a solution for infinite time. And for example, if all the gammas are positive, or if all the gamma, if no two of the constants gamma L are equal, then I guess if they're all, if none of them sum to 0, if there's no subset of them who sums to 0, then you can never have a collision. Okay, so anyway, this is my assumption. I have a solution to ODE and no collisions for some time interval. Okay, and so here's the theorem we will spend some time proving. And okay, and so I'm given this this solution of the ODEs, and I want to consider a solution U epsilon of the Euler equations here. And I have initial data U epsilon 0, and all what I really care about is the velocity or the vorticity. And so the initial vorticity is here. And what does it look like? It's, well, so if I could draw, I didn't really leave myself room for a picture, but let's draw a small picture down here. And so if I have some, say 3 points, then I ask that the, and so I may have on the previous page a PM with strength gamma M, and M goes from 1 to 3 in this picture. Okay, and so I assume that the initial vorticity is supported in a union of balls of radius epsilon around these initial points. And I assume that the integral of the vorticity, of the initial vorticity over that ball is the vortex strength for that that I prescribed before for that ODE. And then also, so the condition here is I don't want the vorticity to change sign in each ball. And so if gamma 1 is positive, then the vorticity is non-negative in this ball. If gamma M is negative, then the vorticity is non-positive in that ball. So the vorticity doesn't change sign within any ball. Okay, that's this assumption. And so these specify a sense in which the initial vorticity is close to being a sum of point masses of mass gamma L at the points P and PL0. Okay, and then so one condition is that my initial vorticity looks like a sum of point masses, sum of delta functions. The second condition is I need some norm bounds, and these are pretty weak bounds. And so I think I emphasized this on the next page, but I'll say it here. I'll say more about this, but so I just need some LP norm of the vorticity to be bounded in powers of this epsilon and negative powers of epsilon. And here P is bigger than 2 for reasons we'll see. And so then, okay, so remember T star is the possible time of first vortex collision. And so if T star is infinite, if there are never any collisions, then I can have any finite T. Anyway, for any time until there's a collision, and for any, okay, we'll see beta below here. Actually, it's hard to see. But for any beta less than half, there's this constant such that, there's an epsilon such that if epsilon is less than epsilon naught, then there are, so here's the point. Oops, I have a terrible misprint here. But what this says is that the vorticity at time t, so there exist these trajectories. P, so Pm epsilon is the epsilon approximation of the mth trajectory, Pm. So the support at time t is contained in a small ball around this epsilon approximation of the mth trajectory. And my terrible, terrible misprint is here. This should be the, a ball whose radius is epsilon to the beta centered at P m epsilon of t. Okay, and so at time 0, I assume concentration of ball, the supportation of ball raised to epsilon, a small ball. At later times, I can't do better than confine it into a ball of size epsilon to the 1/2, or maybe a little bit bigger. Okay, and so that's the role of this beta. Of course, making beta smaller makes the ball bigger. But we can get as close as we like to the square root of epsilon at later times. And then again, there should be a P j epsilon of t. So and then if I look at the vorticity concentrated in this ball of size epsilon to the beta around the approximate trajectory, then that's the amount I started with. And so the ball gets bigger, it moves around, and it contains the whole initial vorticity of the jth ball. Okay, so that's one assertion. So we lose size. So we go from epsilon to a bigger power of epsilon, smaller power of epsilon meaning bigger ball. But the solution retains this structure of looking quite a lot like a sum of delta functions, and it retains the masses of the delta functions. Finally, the epsilon trajectories are close to the trajectories given by actually solving the ODE. Okay, and so this is a very satisfactory theorem. It's valid for any time up to the first collision time. It tells us it has estimates, right? It says that the approximation for the epsilon approximation, the trajectory stays of on order epsilon, and I probably need a time. This probably depends on t. I think I misstated that actually. We'll see later on, but so the control decays as time goes. But nonetheless, it's a good control, and also we have these very weak hypotheses. Here's the remark about the hypotheses. So the natural scaling is the natural initial data looks like is to say omega epsilon 0 is, well, I take some omega naught and I rescale it in a way that preserves the L1 norm. And so something that looks like this in each ball, omega naught has integral gamma sub m in the mth ball, and then I rescale it, and I'll have something who lives in a ball raised to epsilon, and who has the right integral. And so I can see here this would have L infinity norm of order epsilon to the minus 2 and L1 norm of order 1 until by interpolation we have this as p gets closer to 1, the norm blow up is weaker. Okay, so we can see that the in the theorem they can take any power at all. Right, the initial vorticity can blow up like any power, epsilon to any negative power. And so it can be really huge. And so in this way, it's really a striking theorem. As I mentioned, there's a different approach, a constructive PDE approach. And there they really construct the data by hand, and it always has this form. I mean, it has basically this form. And so it can only, it has to blow up slowly. It has to, I mean, the norms have to diverge, like, say, the M3 norm would be like epsilon to the minus 2. Okay, and another remark. So I wrote here that these, so the theorem says there exists an epsilon naught and a k. So epsilon naught, the role of that is to say that the conclusions are valid whenever epsilon is less than epsilon naught, and the k appears here. But the point is, these depend only on the quantities up here. So in particular, well, they depend on, on the trajectories, on the initial conditions and how long I go in time. So it depends on the whole trajectories of the ODE. But then it depends on the what is P, and this gamma should be, what's gamma? Well, gamma are these things, and then this beta should be, I think, alpha. So, sorry, here's what I want. This should be alpha. So, so the constants depend on how badly the norm is blowing up in which LP space. And they depend on the size of the ball in which I want to see the vorticity concentrated. That's what the beta is doing. But the fact that they only depend on these LP norms is telling us that, morally speaking, this result should continue to be valid if I only assume my initial vorticity belongs to LP for P greater than 2. And in fact, this is true. Remember, the step is if the initial vorticity is in L infinity, if it's bounded, then we have existence in unique Euler equations. If it's in LP for P less than infinity, I don't know if I said this, but in fact, one still has existence, just no longer uniqueness. And so the interesting fact is that one can use this control that depends only on the LP norm for P greater than 2 to prove a theorem like this for things with initial vorticity in these LP spaces where uniqueness is not guaranteed. Nonetheless, the solutions, at least there are certain classes of good weak solutions, they have to have these point vortices who evolve in the right way, so to speak, even without uniqueness. And an interesting question is whether this is true also for, well, I mean, interesting if you if you find it interesting, is whether this is true for LP if P is between 1 and 2. Okay, so that's about the theorem. And let me describe the strategy. Okay, good. So here's the approach. Okay, here's a picture of the initial data. And so let's say, and so I have these concentrations of vortices and balls. Let's say U epsilon is the solution as described above in the statement of theorem. I consider the initial data who's with vortices in these balls. I solve the Euler equations. I appeal to a theorem that gives me a unique solution. And let's call these. Let's say this is the initial data is omega epsilon 0 is the initial vorticity. And let's write this as the sum of omega epsilon m0, where little m goes from 1 up to capital M. And this is, and so those would correspond to each of these blobs. And so omega epsilon 1, 0 would be this one, and this would be omega epsilon 2, 0, and so on. So I just, these are the initial blobs. And then we know that, okay, by definition, omega is the curl, the orthogonal gradient of U, And also we know that we can recover U from omega by the Biot-Savart law. And so we know that U just symbolically is the, and so this is a relationship that holds at every t. And let's define, I need several definitions. Okay, so x epsilon of alpha and t is the flow map given by dx epsilon dt is u epsilon of x epsilon and t, and at 0 this epsilon is the identity map, so that's the same as always. And then and remember, we know that the vorticity is transported by this by the flow, and so the vorticity at time. Well, okay, I'll write it down in a second. So let me also define a epsilon of x and t to be the inverse of. Let's write it this way: a epsilon at time t is, I look at x epsilon at time t, and I look at the inverse of that map. Okay, and so x is the map that takes the initial position and carries us to the position at time t. A is the map that takes the position at time t and carries us back to the initial position. And so we know that the vorticity at time x and t is the initial vorticity at the corresponding label. Okay, that's the vorticity transport. And so what I can do is, I'd like to just define let's let time evolve. This flows over here. We can imagine these flow around. And I'd like to think of these, I'd like to call this omega epsilon 1 at time t. And so how do I define that? I'll define, I can just take omega epsilon m at time t. Let's see. At x and t will be omega epsilon m0 at a epsilon of x and t. Okay, and so this exactly says that I look at the points who started out in the support of this in the mth blob, and I ask. So I look back at time 0. I ask, was x in the mth blob? If yes, I assign that vorticity. Okay, and so here we're really just I partition the vorticity up and I ask how each piece moves. So omega 0 epsilon m is omega epsilon 0 times the curvature function. The function is 1 on the ball around of size epsilon around the point p0 m. Okay, that's the definition. Okay, and so then I partition the vorticity up into m pieces, and then I define u epsilon m to be the velocity, the part of the velocity who is generated by the mth vortex blob. Omega epsilon m. Okay, and so good. And so then, so note that the whole vorticity at time t is just the sum of the omega epsilon m at time t, and similarly for u epsilon. So when I write down identity, I mean it's true for all x and t, in fact. And the equations are, well, I can just write as a, I'm making things complicated. I can take my former equation, the Euler equation for omega and u, and I can write it as a system for omega m and um. And so dt of omega epsilon m plus u and this should hold for every capital M. And so what is this? And so we know, did I write on Euler? So what I really want is for this to be u epsilon, right? So each piece is transported by so I partition the vortices into blobs, and then each blob is transported by the velocity field u epsilon, who solves the equation. And so I define f epsilon to be the sum over L f epsilon m of u epsilon L. Okay, and so what this says is that I haven't done anything at all fancy. I've just said I partition the vortices into m pieces, and the mth piece solves an equation which says it's transported by a flow consisting of two parts. One is the part that it generates itself, and so u epsilon m is the Biot-Savart kernel applied to omega epsilon m. And then there's the piece generated by all the other vortices. And so the way we want to think about this is, I'd like to forget the structure of this f epsilon m and just view this as some given external vector field. Okay, I think all this is down here. And so anyway, here's the equation again. Right, so I'd like to say, I'm going to treat this by for now, initially forgetting where f comes from and just say this equation has this form down here. So there's some vector field f, and I'm going to draw the subscripts to make the notation less burdensome. There's some vector field capital F, and let's assume for now it's given, and I'll study this equation. And so here u is the so secretly I'm thinking of omega as corresponding to a single blob in this decomposition, but I can forget that and just study equation 4. And then let me assume that the velocity, that the vector field f, the given vector field f in this, and so here, in other words, I've reduced this question of studying the Euler equations with the background flow. And the background flow is secretly the one generated by other vortices in this decomposition. But forgetting that for the time being, we just assume we have a smooth background flow, it's divergence free. That's natural given the above discussion. And it's Lipschitz continuous, and I don't want a t here. If we wanted to make life harder, we would have the Lipschitz constant depend on t. It's Lipschitz continuous, and there's a uniform Lipschitz bound for every t. And I want to then study this equation. And what I want to do is, especially to take initial data with just a single blob of vorticity, a single concentration of vorticity, and ask how does that evolve? Okay, and I'll just have time to state theorem. I'll state a first theorem. But earlier on I said this result about point vortex dynamics in Euler if I have m initial data. So almost all of what we discuss will be this model problem of the Euler equations with a background flow and with a single concentrated vortex. Okay, so that's what we'll focus on for the time being. And I'm going to state a theorem, which is the first result. Let me say, all the stuff I'm doing, all these works, there are a series of papers written by Marchioro and Polverenti in 85, maybe. And then another paper by Marchioro and Polverenti in around 94. Mark Yoro is the sort of the constant in all these things. He wrote papers with Mark Yoro and Caprini, Mark Yoro and Buta in the last few years, improving the results and improving the things. There's a recent paper by Chechi and Zeiss, which proves some version of this theorem for initial data in LP with p less than infinity, p greater than 2. And so that's also informed the approach I'm taking here. Okay, and so I'm presenting the work of those guys. And so here's what I'd like to do. So I assume I take it, so I'm gonna, so I imagine I have a single blob concentrated on ball raised epsilon. The epsilon doesn't actually appear in these first theorems. So the initial data, I'll call it omega naught. Let's assume it's bounded. And I want to assume it doesn't change sign. So it's either non-negative or non-positive. And so then let capital omega be the integral over omega naught. And so then omega over omega is a positive function, a non-negative function whose integral is 1. So it's if you like, it's a probability measure. And so in all these expressions, p and I, you see a little omega divided by capital omega. So I'm integrating with respect to a probability measure. Okay, and so then, P of t is, this is like if you like, the average position. This is the first moment of vorticity. And so if omega were a delta function, if little omega over capital omega were delta function, this will give you exactly the position where it's located. If it's concentrated, it will tell you where it's concentrated. And so we want to think of this as being sort of the approximate center of vorticity. And then this I of t is a crucial quantity. It tells us how concentrated is the vorticity around its center of vorticity. And so if, for example, the vorticity is concentrated in a ball raised epsilon around a certain point, then we can see that if it's concentrated in a ball raised epsilon around the center of vorticity, then if it's entirely supported there, then this x minus p squared would always be of order epsilon squared, where the omega is non-zero. And so this would then be a quantity of order epsilon squared. So this tells us, again, the scale of, say, the square root of I is something like the scale, the length scale of the vorticity concentration around its center of vorticity. Okay, and so the theorem will prove, I've copied the definitions up here, okay, just for reference. The theorem will prove is, so here P star, what I wanted to, I'd like to compare, well, I can see as I solve the equation and the vorticity moves around, this P at time t will tell us how the center of vorticity moves. I'd like to describe that. And what this does is it gives an estimate in which we compare the center of vorticity at time t, P of t, to this P star who is found by solving an ODE. And the ODE is the one that says exactly just that the point P star moves with the background flow F, right? So the velocity of P star is the function, is this vector F evaluated at the point P star time t. And then if I need this, well, if I have this, I guess, then I don't need both this and that, right? If I have this assumption, then this is 0. And if I have, so let's get rid of this. So if I want, I can always assume this is 0, and then that will make my estimate a bit better. Okay, and so what does this tell us? And so we want to think of initial data for which the I of 0 is order epsilon squared. That's what the data I considered in the bigger theorem looks like. And so, so the vorticity concentration length scale is order epsilon initially. And this says that it may grow as a function of t, but at later times it's still epsilon times a constant who's growing, but it's still concentrated in the same epsilon scale. And the difference between the ODE trajectory And the center vorticity is also of order rational, if this is, again, epsilon squared. Okay, so that's the first theorem, examining a isolated vortex by itself. It has a beautiful, easy proof. And then the, well, I'm kind of out of time, but this is, it's a substantial progress toward the goal, the main goal of describing vortex dynamics in this more complicated situation with n initial blobs. But it also leaves a lot of issues unresolved. So we'll have to, use this, prove this, and then see how it's a starting point and what remains to be done. Okay, thanks. That's it for today.